In this video, I'm going to walk you through the unit storyline for Unit C1 developed by OpenSciEd. All right, so this unit is all about sea level rise and how it relates to climate change and carbon dioxide in the atmosphere. We get into ideas about light energy and heat and energy transfer. We also develop ideas about density and specific heat, and we calculate the amount of energy transfer to melt ice in a glacier. So that's kind of the big picture. If this is the first unit you're teaching in OpenSciEd for chemistry, and you've been teaching chemistry for a while, or even you took chemistry in high school or college, this is going to feel really different. And the reason is that this is an integrated unit where we are bringing in earth science standards, and we're going to use an earth science anchoring phenomenon to anchor the unit. And we need to use the chemistry ideas to explain what's happening here. So it's going to feel a little bit like earth science in the beginning, but realize that the chemistry is necessary to be able to explain what's happening. And so this is really an introduction to how we integrate the two domains together. So trust the process, stick with it. There will be some OpenSciEd units that are straight physical science, but this one has a good chunk of earth science, and so does C5. So hang tight and let's walk through it and know that there is a reason for all this earth science in our chemistry classes. I want to point out these icons right here. They actually help you understand which routines you're using from the storyline model. So you'll see in lesson 1, we're using the anchoring phenomenon routine. And very rarely does this happen, but we also are going to do some of the anchoring phenomenon routine in lesson 2, as well as adding in an investigation of using some data. Now, you will notice that there's 3 days that this anchoring phenomenon will take, plus another 3 days in lesson 2. So there's significant time that's put into developing this anchoring phenomenon and getting students to understand what we're trying to explain using a chemistry lens. Now, in lesson 1, we're going to answer the question, how are sea levels rising and forcing people to move? And so we look at 3 focal communities. One is in Louisiana, the other 2 are in Africa. One is Senegal, the other is Sierra Leone. And we're going to watch some stories and some videos to help, first of all, put a human perspective to it and see what's happening to people in these areas, but also try to get students to start thinking about why this is happening. We're going to look at some related phenomena, which are going to kind of bring into picture some ice and sea ice and land ice, and starting to kind of guide students in the direction to think about that polar ice might be the reason that sea level rise is happening. And so students first draw an initial model. You can see it represented here. And then we share these models with one another, and we come back together to make a consensus model, trying to figure out at the particle level what's happening here to explain the polar ice melt and how it's affecting sea level rise. We're also going to bring up the ideas of energy transfer. We're going to use that lens throughout the unit, and we're going to draw multiple energy transfer models as we try to explain this anchoring phenomenon. In lesson 2, we're going to be looking at some data, historical data from the past, and we're going to be looking at polar ice volume and temperature of the air or the atmosphere. And so we will see that the atmospheric temperature is going up, but the polar ice volume is going down. And we start to kind of think about what evidence we are using to support this and how this might relate to carbon dioxide and how carbon dioxide is affecting this, including human activity, maybe releasing carbon dioxide, plants absorbing carbon dioxide. So we start to think about how carbon dioxide relates to this data. In lesson 3, we're going to go deeper into carbon dioxide, and we're going to answer the question, how does carbon dioxide contribute to climate change? And you can see we've got more energy transfer models here. We got the dotted line represents a boundary. We've got arrows showing the movement of energy. This is going to be developed throughout the entire unit. We're going to make a list of key model ideas of energy transfer. And so there will be a lot of energy transfer modeling in this unit. In this investigation, you can see there's 3 heat lamps set up. We have 3 bottles. It's called the closed bottle investigation. So we're going to put caps on those bottles. The first one is just regular atmospheric carbon dioxide. The second one has an increased level of carbon dioxide. And then the third one has even more carbon dioxide. And that comes from Alka-Seltzer tablets that we place into the water. And so we are going to find out that carbon dioxide does enhance the temperature of the atmosphere, the increase in temperature. And so we're not sure why yet, but we do know that carbon dioxide is contributing to this increased temperature. In lesson 4, we're going to start thinking about land ice versus sea ice. And we realized that in some of the models we're looking at or some of the simulations that the sea ice isn't represented. So we do a little investigation and we see that this is some modeling clay with an ice cube on top. That represents land with ice on top. This is sea ice, so the ice cube is straight in the water. And we realize that the volume of the water does not change in the sea ice. We don't get into anything with displacement, but we realize that since it's already in the water, the volume does not rise. But in land ice, obviously, when it melts, the volume rises. And so that's a quick investigation to maybe tackle some misconceptions that the icebergs are contributing to this. And you will see that in models. Students will put icebergs in their models, but land ice is the real reason for this. We then use some mathematical modeling and we calculate how much sea level rise would happen if all of Greenland's ice melted, and then if all of Antarctica's ice melted. And we realized that it could rise between 6 and 55 meters. And so this would absolutely affect cities across the world. In lesson set 2, we start to think about how we can help solve this problem or how we can mitigate sea level rise. And so we are introduced to 2 different solutions. The first one is microbeads. And so microbeads are spread out all over the young ice in the spring months, like right after winter, after all the snow falls, right before the melting starts. Some microbeads are, a layer of them are placed over the snow. And the second one is a berm solution. And so you can see here, there's a diagram of this glacier that actually contributes to the most ice melt in Greenland. And so we're introduced to this glacier and we see that there is a berm solution. It's kind of like a wall or a big hill that's built in front of that glacier. And so we're trying to figure out how the microbeads and how the berm solution are actually helping slow the ice melt. And so this is actually some initial modeling. We're going to go back to some initial ideas. We're going to have some energy transfer models. And the kids actually split up into 2 different groups. They try to figure out what the solutions are, but these are just initial ideas. We're then going to go in and actually try to investigate to figure out how to explain how these will reduce ice melt and mitigate sea level rise. We then look at first the bead solution, and we're looking at different colors, and we read an article about light colors and dark colors and how they reflect and absorb light differently. We are realizing that there's an albedo effect with the white snow, and so it reflects a lot of the light energy back out into the atmosphere. And then the dark materials absorb these particles and infrared light over time. We then relate it to carbon dioxide and other greenhouse gases and their ability to reflect and absorb the light energy and the infrared light, and how the carbon dioxide traps it in the system. It re-emits it into the system and traps it. And so we introduced the idea of feedback loops and how a change can either be exacerbated or return to equilibrium, depending on, the effect of what happens with either the design solution or anything else out there in Earth's systems. And so when we move into lesson 7, we're going to go deeper into feedback loops. We're going to use an infographic to really develop the idea of positive feedback loops and negative feedback loops. And there's some modeling that happens with this. And then there's a transfer task. And so a transfer task is when the science ideas that have been developed so far in the unit are used in a new context. And so the new context is permafrost thaw. And so they're given an example of this permafrost thaw, and we are going to explain how this is affecting the original change in a feedback loop. And they identify that it's a positive feedback loop in the transfer task because when the permafrost thaws, it releases more carbon dioxide, and then that heats the atmosphere more, which then, of course, thaws more permafrost. So that is figured out in the transfer task. In lesson set 3, we're going to go deeper into the other solution, which is the berm solution. And so we want to know how well that berm solution would work in the context of Earth systems. The first lesson of this third lesson set is going to answer the question, what is going on where the ice meets the water? So we're provided with a diagram that shows the ice is this white area, the water is the blue and the red, and that's a temperature variant. And we look at some data that's collected from NASA experts, and we use some indigenous knowledge from the people who have lived there throughout history. And all of this is leading to the idea that they think that the warming ocean is causing this ice melt. But what we are noticing is that the warmer water's on the bottom. And that is very curious because we know from a lot of our science in the past that we have learned that warm air rises, cool air sinks. And so this is actually kind of confusing that it's the opposite. And so we are going to go deeper into investigating this basically phenomenon using density as the lens. So in lesson 9, we do an investigation using different amounts of mass and volume, and we really develop the idea of density. Instead of just giving the equation, we really show that linear graphing of volume and mass to show that density is the same no matter the amount of volume or matter the amount of mass. It's going to remain the same. It's a property of the substance. And we're going to then go back and think about the glacier and how this density is helping explain how the glacier is melting. There is a demo, which is a density column. So you have that warmer salt water on the bottom and that cooler fresh water on top. And what we realize is that that ice melt is creating a cold layer of fresh water on the top while the warm salty water is flowing underneath, and it's actually carving out the bottom of the glacier. And so this really helps, this density idea really helps explain why that warm water is melting the iceberg underneath and it's calving or caving in and making it fall. In lesson 10, we're going to really develop the idea of specific heat. And we do this through a couple different investigations. And the first one is using a simulation. And we use different masses. And we notice that when two liquids are interacting that of different temperatures, that they're going to eventually meet equilibrium at a temperature somewhere between the two. And it is dependent on mass. Where this temperature is going to fit. And so we are going to develop this idea of this equation here that energy transfer can be calculated. As long as you know the specific heat, the mass, and the temperature change, you can actually calculate the amount of energy transferred. And so we're going to use this equation as we move into lesson 11, and we're going to try to figure out how this new heat equation fits into our energy transfer model. How does it help us explain how much energy is being transferred into that glacier and how the berm is going to basically how much energy transfer is going to not happen because of that berm. And so we do another investigation where we're looking at mass and temperature and the mass of the melting ice. And anyways, it's a pretty common specific heat experiment. I think some chemistry teachers have told me they've done this in the past. And so we're going to graph our results. We're going to see that line of best fit again. And we're going to then take all that information and bring it into our berm solution at the end. This is a transfer task, but it's what we call a near transfer task, which means we're going to take the science ideas we've developed the whole time, but we're actually going to use it to explain the anchoring phenomenon. And we're going to calculate how much energy that berm is going to stop from transferring to the glacier. And so we are going to annotate a model, and we're going to do some calculations, and that will be an individual transfer task for students to really explain this berm solution. In lesson 13, we're going to go a little bit deeper into a more global picture and how these systems interact across the world. We're going to talk about how climate models can be used to predict energy transfer, kind of like how much sea level rise will happen. We can calculate that because we have these mathematical models and we know how things interact. And so this one we're going to be using, this is a SAGE modeler. All of the components are already downloaded into or uploaded into the system. And so they manipulate the SAGE modeler to see how the different components affect each other. And then we also come back to how this will negatively impact the people around the world. Now, the very end of this lesson, of course, we're going to go back to the driving question board, see what questions we've answered, how we feel about all of this stuff. But we're going to end with another transfer task. This time, the new context is a heat pump. And so we take all the science ideas figured out throughout the whole unit and we apply it to an entirely new scenario, which is a heat pump. So hopefully that gives you a pretty good picture of where that chemistry is going to fall into place in each lesson to help us explain that anchoring phenomenon.